Hi, this is Gleno, people, and yeah, I know you haven't heard from me for a while. I've been, a bit busy with work and doing geometry, working out the the drop over certain distances over Earth curvature. Yeah, because that's what normal people do, working out drop over curvature. All right, geometry. All right, something that everyone hates at school. And thinks that they'll never use, and here I am doing it at the age of 44. I'm just like sitting there doing this geometry, right? And I've been reading physics books. I've been reading Isaac Newton's Principia. So anyway, I'm sitting there doing me geometry at the table, right? And I get a knock on the door, and I was thinking it was a friend of mine or something, and I thought, yeah, I'll go and answer, because that's the polite thing to do, right? And I open the door, and I'm a bit surprised because there's these two Mormon dudes, right? These two missionaries standing at my door. And before they could even get a chance to show me their Book of Mormon, I said, "You guys, any of you guys know anything about geometry?" And the Filipino guy's like, "Yeah, I know how to do geometry." I'm like, "Okay, I've got a problem for you to solve." And they're like, "All right, that sounds cool." So, so the following piece is basically what transpired, right? I went and grabbed my papers and equations and things I've been working on, and this is basically what happened, right? Okay, so I was just trying to show them this problem. Excuse the drawings; they're pretty primitive looking, like a 2-year-old drew them with its mouth, But and then also excuse the fact that I've gone over some earlier calculations. I've drawn over them, so it's a bit messy, but you'll get the general gist. All right. So I was showing these Mormon dudes this geometry problem I was having of transferring a spherical geometry problem to an oblate spheroid, right? And they said beforehand that they could help me, and now once I showed them the problem, they're like, "Oh, sorry, we've got no idea how to help you with that one." I'm like, "Yeah, no, that's cool. Not everyone's like Isaac Newton or something." So anyway, then I started drawing. I drew the Earth's apparent orbit around the sun, right? And got a little drawing of the Earth there going around the sun. And it's got the aphelion, which is the furthest point away from the sun, which is about 94 million miles away, sorry. And the perihelion, which is approximately 91 million miles away in front of it, right? Which gives us an average of around about 93 million miles distance from the sun. Okay? Now, I try to explain to them, all right, that in order for us to maintain angular momentum, we'd have to keep a sort of constant speed, right? Or constant velocity, or even constant acceleration, etc. And they're like, yep, we agree with that. So as you can see on this diagram, you can see the Earth, and I've written there that it's revolving at around about 1,039 miles per hour, which is pretty easy. You just sort of like use the circumference of the equator, and then you divide that by 24 hours, and that gives you approximately 1,039 to 1,043 miles per hour. That any spot on the equator you'd be travelling at, right? So they say, yep, about 1,000 miles an hour. Yep, cool. And then I said, well, and on top of that, we're orbiting the sun, right? So in a whole year, it takes a whole year to orbit the sun, right? Now, if you take the mean distance from the sun you know, has a radius of 93 million miles. And then you take that figure and multiply it by 2 pi. You get 584,336,212.74 miles that we're doing in 365.25 days, right? So not only are we rotating at 1,039 miles per hour, we're also rapidly moving around the sun in an elliptical orbit around the sun, right? Approximately 66,659.39 miles per hour, right? That's what it averages out to, the average speed. It's 66,659.39 miles per hour. And they're like, yep, cool, yep, that's right. Okay. Now that's calculating it at the sun being in a state of rest, right? The problem with the whole theory is the fact that the sun is apparently moving, and it was Galileo who came across this discovery by looking at sunspots and determining that he determined that it was moving. And so they've calculated it to be moving at around about 483,000 miles an hour. And they're like, yeah, that sounds about right. And it's sort of orbiting the Milky Way, and that's all orbiting the Great Attractor, right, etc. And so I said, okay, so the aphelion is the furthest distance we are away from it in our orbit. So in order to catch up with it, we'd have to accelerate, right? And I said, yeah, that makes sense. It's sort of like, you know, you're going to overtake a truck that's going 100 kilometres an hour safely on a road. You want to be going faster than the truck. You wouldn't want to be sitting next to it. Otherwise, it's going to smash into you as it goes into the merge lane, right? So you have to be going faster than the truck, okay? And that's the same here. If the Earth is not going to sort of ram into the sun, it would have to be going faster than the sun, which is 483,000 miles per hour, right? In order to get to the perihelion, which is the closest distance to the sun. And then as we go around there and go back towards the aphelion, we're apparently decelerating. So we're going slower again. So I said, how is that possible, right? How is it possible that we could be accelerating to more than 483,000 miles per hour while rotating at 1,039 approximately miles per hour, right? And not feel it? They're like, oh, space. And I said, okay, we'll keep going with this. All right, so the Kobe satellite, or Kobe, or whatever you want to call him, this satellite they apparently sent up in 1989. It sort of measured our velocity or our speed in relation to, or with the point of reference being the apparent radiation from the Big Bang, right? And they have estimated that we're pretty much going at 242.3865 miles per second. Right? Yep, you heard right? 242.3865 miles per second, which gives us 872,591.4 miles per hour. So that's how fast it calculates that we are travelling at. Okay, so if we're moving at roughly 872,591 miles per hour, as well as rotating 1,000 miles per hour, why aren't we feeling it? And they're like, oh, space. And I said, okay, well, this actually defies what Isaac Newton had observed. You see, he observed that because of the Earth's rotation and the actions and of the sun and the moon upon it, uh, even though this is all in space and from 93 million miles away. Apparently the equator is expanding and the poles are being squashed together, just slightly, causing us to become more of an oblate spheroid. And they're like, yep, we understand that. That's what he said, right? Yeah, cool. So how does that work? If you're in space where apparently your movement doesn't get isn't affected, right? Doesn't affect you, then how is it possible that it could affect the mass of the equator? Like, most of the equator is basically made up of heavy mass, land mass, right? How is that expanding? How is that affected, but we're not affected? How is the centrifugal force affecting large landmass, but is not affecting human beings, right? They're like, oh, wow. Yeah, and then I tried, as you can see by this next picture, I tried to show them a picture of what they try to teach us at school. You know, they get the bucket and they fill it with water and they say, okay, spin this bucket and we'll show you what centripetal force and gravity is all about. So we're spinning this bucket and we're like, wow, the water stays in the bucket, right? It just happens to stay in the bucket. Well, the only centripetal force that's in that bucket that's keeping it bound to the center is the bottom of the bucket. And so I drew this picture, and then I said, how about if we drew holes in the bottom of this bucket? What would happen if we swung a bucket of water around us, right, with holes in the bottom of the bucket? What would happen? They said, well, water would go everywhere. I said, yes, that's right. Okay, water would come, soaring out the holes in the bottom of the bucket. Not even our atmosphere would be able to, keep it in. I said, so how is it possible that we could be spinning and moving at this kind of velocity and the oceans aren't just flinging off this imaginary ball, right? And they're like, oh, we don't know. And I said, well, of course. And I said, now imagine a gravitron. So you can see my picture of a gravitron. It's pretty scientific. And I said, how fast do you think this is rotating, like the inside of this? And they said, well, we don't know. I said, well, it's approximately like 45 to 46 feet in circumference, like on the inside, right? And it uses 44 panels of about a foot wide. Okay. Now it does 24 revolutions per minute. It gets up to about 24 revolutions a minute, which means that at any point in that gravitron, here, listen to this. At any point in that, if any point of that gravitron, you'll be traveling at about 12.5 miles per hour. That's right, 12.5 miles per hour, which is nothing, right? And I said, but imagine chucking, and as you can see, I've got the gravitron on the back of a truck, right? It's kind of funny. And I said, imagine it was on the back of a truck and it was moving and you're in the inside. And this truck was also doing circle work, right? Doing some big elliptical circle thing. I said, how much centrifugal force would that create? And they just looked dumbfounded, right? So I'm sitting there saying, look, what happens when you're on the gravitron or anything like that? Do you fall toward, which direction do you fall? And then one of them sort of goes, oh, I fall towards the center. I said, do you? And he says, no, actually, yeah, you're pulled away from it. And I said, that's true. You see, a spinning object will create centrifugal motion, which means you'll be taken away from the center of the rotation, not pulled towards it. There's no centripetal force. There would be only centrifugal, right? And even more so if it was on the back of a truck. Okay, so that's those drawings in a nutshell. Trying to explain to these guys about centrifugal versus centripetal force, and how it's a lot of bogus rot, right? And how we could not be possibly spinning and traveling around the sun, which is traveling around the Milky Way, which is traveling towards an even bigger system, right? Anyway, so I was just trying to tell them that, and we spoke for about half an hour, right? And then they said, oh, we'll come back. I don't know if they'll come back. You know, I'm not sure if they'll come back, but they said they would, and they'll talk more about it. But I even invited them, I said, look, see that car there? That's my car. I invite either of you to stand on the roof while I do some circle work, and we'll see whether you fall towards the engine or whether you fall towards the back end of the car, away from the car. And they're like, nah, we're good. Ha! No, we're good. You know, they didn't even have the balls to stand on the roof of my car while I was doing circle work. I mean, what kind of scientists are these people, right? So as you can guess, I was pretty bummed that they weren't willing to sacrifice their limbs for the sake of science, right? Okay, but I'm pretty sure I'll get over it. But let's get back to what I was sort of talking about in the introduction, right? About Isaac Newton and his book Principia. It's got a lot longer title than that in Latin, right? Mathematical Principles of Philosophy or something. All right. So anyway, we're sitting there reading this thing. I'll show you the cover, right? It looks like this. And as you can see, this book is pretty heavy, right? But this is what I've been reading while I've been doing all my geometrical equations, okay? Excuse my throat, it's a bit sore at the moment. Just coming down with a cold, but that's okay. Bit of cold weather never hurt anyone, right? So anyway, he came out with his theory of gravity, okay? It's about gravity, this book. And he came up with his theory to try and explain Kepler's ideas, all right, that how the planets apparently do, and including Earth, apparently do elliptical orbits around the sun, and that they one of the laws of this theory was that they had to sweep out equal areas in equal amounts of time, okay? And that they had to continue to maintain a constant angular momentum. All right? Excuse me. So, in his author's preface, Newton writes, I hope the principles here laid down will afford some light either to this or some truer method of philosophy. See, he did have some doubts about this. No, he had some loose ends that he needed to tie up, and he sort of really couldn't. But he tried to leave it he wanted to leave it to better people, not necessarily better, but people who down the track might have accumulated this knowledge, extra knowledge, and been able to look at it in a different light and given a more truer account of what was happening. So anyway, that's what I'm seeking to do. So in his axioms, which is one of the chapters, axioms or laws of motion, the very first law of motion states, every body perseveres in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. You see, this is why he came up with the idea that we must be an oblate spheroid, okay? Because the sun and the moon and our own rotation is pulling at the equator, causing us to bulge at the equator and sort of get squashed just slightly at the poles, okay? And I think he saw the problem with this. That if the sun and the moon were able to do this sort of thing to us, then of course it's going to uh, change our state, all right, and therefore most likely have an effect on our uniform motion and our right line, right? It's going to affect that. But anyway, because of this oblate state that we're apparently in, right, he theorized that at the equator, gravity is lighter than it is at the poles, okay? And some of the experiments that he sort of did try and find this out, and it doesn't sound very scientific, but it sounds quite crazy, really. All right. He used a pendulum, right? So they'd get a pendulum and they'd sit it next to a clock, or they'd time it or something, and they'd get a chicken, right? And if they time it and they'd see how far it deviated from certain time or whatever, and determine how much gravity is acting on it, right? I mean, to find out if gravity was working or not working, if it was heavier at one place than another, then I could think of better things than a pendulum, yeah? I mean, in those days, they might not have had dumbbells or anything, but they would have had, like, weights and scales, right? For commerce and trade and stuff, they would have had weights. They could have just grabbed a weight. They could have grabbed a scale, right? They could have gone to Ecuador, and they could have weighed it there. Then they could have, like, sailed over to freaking Russia or something, and then they could have weighed the same thing with the same scales. And if it was out, then they could prove their theory. But they didn't do this. They used a pendulum, okay? And they discovered that gravity was lighter at the equator, okay? But then someone wrote to him and said, you know, like, dude, pendulums are made of metal, you know, and they're susceptible to fluctuation. So, you know, like, you have it in a colder climate, it's going to constrict, right? So the metal will shorten, thereby giving it a quicker swing than if you were to take it to a moderately warmer weather or tropical, you know, where the metal would expand, causing it to tick slower. So it would affect the outcome of this experiment, right? And of course, he sort of put this in the back of his book, you know. He sort of acknowledged that was one of the problems. And another one of the problems was that Paris, which is about 48 degrees plus, you know, above the equator, that Paris itself was experiencing lesser gravity according to pendulums, okay? So it doesn't sound very scientific. As I said, I'd rather grab a 10-kilogram dumbbell nowadays. I'd grab a 10-kilogram dumbbell, I would weigh it in Australia, then I'd take it to Ecuador, and I'd weigh it there, and if there was any fluctuation, then that would prove their theory right. If there wasn't any fluctuation, then it goes to prove it's rubbish, okay? But, you know, if their theory was right, then there wouldn't be a uniform 10-kilogram dumbbell on Earth. There wouldn't be a uniform 10 kilograms. That means that if I was to get 10 kilograms of meat in Australia and try to sell it in Ecuador as 10 kilograms, they wouldn't buy it because it weighed 9.5 kilograms. They'd say, you're robbing us. Okay, so the whole so-called global marketing thing, right, wouldn't work. It wouldn't work because everything would weigh different, right? So that's one indication of why I think this is rubbish, okay? I call bullshit, all right? So anyway, moving right along. Another reason why I sort of really have a problem with this whole idea, right, is, as I stated to these guys, that we're moving apparently around the sun at incredible speeds, right, which is moving itself at 483,000 miles per hour towards a great attractor, which is itself moving towards Shapley supercluster. Take a look at this picture, right? Yeah, that's right. This Shapley or Shapley supercluster is apparently the biggest thing in the universe at the moment, right? So we're all revolving around it while revolving around the sun, you know. And lucky for me in Australia, this supercluster just happens to be sort of like in my sky, right? Right above my house. I'm looking above my house and I see the freaking Milky Way and I see the Norma cluster, and right up there is the Shapley supercluster. So we're actually going south first to the supercluster, right? And it's right above me, so lucky me, right? Okay, this is what I don't think is right, right? Okay, is that the fact that we're moving at this such greater velocity toward this thing, right? We'd have to be, right? If we use the Shapley supercluster as a point of reference, and if it's moving itself around another universe or something else or another cluster, then our speed does exponentially increase. Okay. Now, going back to the original point, if that was the case, okay, the equator and the land masses around the equator, if they are bulging because of our rotation and everything else, right, then we should experience the effect or the influence of this. Okay, we should experience it. For them to say that we don't is rubbish. Okay, you can't say cause gravity like so many people say, right? Everyone's like, you know, everyone's answer is cause gravity. Right? Cause gravity. Why don't we feel this? Cause gravity. Why are we still on the earth? Cause gravity. I've explained, you know, anything that's operating in a circular sort of motion is going to cause centrifugal force. And the very fact they pointed this out in regards to the equator, you know, the centrifugal force is actually acting on the centripetal force, which means that gravity is lighter there. See, that goes to prove, right, that there is centrifugal force that would be operating on us. We'd be flying off the planet at that kind of velocity, okay? And the fact that we're not only just going at a uniform speed, we're actually accelerating from the aphelion to the perihelion, okay? We'd have to be. And that's if we were sort of doing this orbit that was sort of going from behind the sun to in front of the sun and all that sort of stuff. I mean, it even gets even more complicated, right? It gets even more complicated when you have a sort of vortexal orbit, right? Where you've got this orbit that's going sort of what's a vertical sort of orbit around the sun. Okay, because not only are we having to like go from the aphelion and accelerate to the perihelion, so it'd be doing really fast speeds in a vertical sort of fashion. We'd also be going horizontally or laterally, right, to keep up with the sun. Okay, and on top of that, the moon would be also having to do the same thing in order to keep up with us. So it's all rubbish, okay? It's all rubbish, all right? Now, if you don't believe me, well, all right, let's just take a look at this picture, okay? We'll take a look at this picture of the Earth. It's a computer-generated image of Earth, and I've compared it here to Russia's picture from space. Well, apparently from space, right? Now this is the first picture is one of Earth it's sort of been modelled after what how the scientists and the physicists have sort of described it, right? It's an oblate spheroid that is a bit more of a pear shape, right? Whereas the other one down below looks like just a glamorized version of the blue marble that NASA came up with, okay? Which was also a CGI picture, okay? All right. Now the first one sort of looks like a CGI picture on the bottom there. Looks like a CGI picture. The top one, the second one, it looks like a mouldy sort of rotten potato that's been thrown in the wash with a tie-dye shirt. Okay. It doesn't even look like a planet. Okay. We couldn't even live on it. We couldn't live on it. And we certainly couldn't live on it if that was trying to like accelerate around the sun. It wouldn't happen, okay? You know, if you're looking at this sort of stuff and they're saying this is science, you know they're talking rubbish, okay? I mean, start thinking for yourselves, people, all right? Don't sit there and say, well, you know, science, you know, because gravity. And don't go sitting there saying, oh, you only believe in geocentric or flat earth because of religion and stuff. That's rubbish, mate. Just have a look at it, okay? Like, you look at, for instance, what Isaac Newton said about, like, atheists, okay? He says, opposition to godliness is atheism in profession and idolatry in practice. Atheism is so senseless and odious to mankind that it never had many professors. So don't go trying to defend scientists when they say that sort of stuff about atheists, okay? Alright, here you are saying gravity and saying that flat earth is all about religion, right? And yet you have this guy who you champion as the champion of gravity and oblate spheroids and stuff. And he's basically saying that atheists are stupid, okay? And they're a blight to humanity, all right? So don't go defending someone who's not going to defend you, okay? It just doesn't make sense, all right? But I'm not here to sort of make enemies here. I'm just trying to point to the truth, all right? Get to the heart of the matter. And the heart of the matter is basically that science has been telling us a lot of lies and a lot of rubbish, okay? And just encourage us all to get out there and do some research for yourself. Look into geocentricity, all right? Aristotle, look up Aristotle and Ptolemy and many others who have looked at different models of the earth and of the universe, and do some thinking for yourself. Don't just accept what teachers tell you or what the scientists have tell you or what the television tells you, you know. Don't get brainwashed. Start thinking for yourself. I hope you've seen sense of what I've said, right? I hope you've seen it and you're thinking to yourself, yeah, that's right. That doesn't sound sensible. That doesn't make sense. That's not rational. Okay? It doesn't make sense. All right? So start thinking for yourself, and I think that by investigating these things, that I believe you will all grow an appreciation for the world you live in. Okay? I mean, there's nothing wrong with appreciating the world you live in and appreciating the people that are in this world, all right? We're all brothers and sisters, and we should all look out for each other and all respect one another, okay? And, yeah, just keep it real, people, and stay tuned, because in my next video I'm going to be looking at, excuse my throat again, I'm going to be looking at flat earth math, okay? There's been a few accusations thrown at it, so I'm going to discuss that and show how I work out drop over curvature, okay? And we're going to be discussing things I've looked at over long distances, all right, myself, because I've actually gone out and done this thing myself. I haven't just listened to what other people have said to me, okay? I mean, I used to be a heliocentrist, okay? I followed, excuse me, theologians and like Dr. Henry Morris, who's a creation scientist, okay? He's the father of creation science. You know, I've read his Genesis record and I've even got his study Bible, you know. And he's all for the heliocentric, and it was only when I started looking into this stuff for myself, you know, that I saw how wrong these people are. You know, even Christians can be wrong, okay? So look into it yourself just as I have, and I'm going to continue to do this, you know, weather permitting. All right? All right, keep it real, and I'll see you next time. God bless.